here we have a circle. Space from here to here is the radius, this distance. The ratio between this length and the length of the whole circumference is circumference equals 2 pi r, where that's r. And this 2 pi r. Now we can get the formula for the radius. Obviously, if we have the circumference of a circle, we get the radius. But we very seldom have the circumference of a circle, because that's relatively hard to measure. Also, we want to get the radius in other ways. Here is a sector of the circle, and I'm going to call this little angle, which I can measure, A, and this arc, big A. Now we want a formula for this, and I'm just going to write it out. R is approximately equal to 57.3 times A divided by A. Make sure you get that point in there. Now how do we derive that? It's really very simple. We can say that the circumference is to 360 degrees as big A is to A. So that's 2 pi r over 360 equals A over the angle A. Now if we multiply by 360 and divide by 2 pi, we get R equals 360 over 2 pi A over little a. 360 divided by 2 pi is approximately equal to 57.3. So, there you have it. Now, one nice thing about this, if A is less than 5 degrees, this also works pretty well for the chord. The chord is the straight line across here, which it's not exactly perfect, but it's pretty good. And so you can use this very quickly if you measure that angle and you have this distance. whether that distance is straight or curved. If it's less than about 5 degrees, this formula works. We're going to talk about curvature. The curvature would be how badly this is curved. So if we have this is a lot of curvature, this is only a little curvature. Curvature is the inverse of the radius, so C equals 1 over R. Curvature is very, very helpful. Very, very helpful concept. A lot of times we don't even really care about R, but we do want to know C. And a lot of formulas work a lot better with C than they do with R. I'll give you an example very quickly. This is the lensmaker's equation. 1 over f, focal length, is equal to n minus 1 times 1 over r1 minus 1 over r2. Okay? But if we can just subtract this, if we can convert these to curvatures, we have power. We have power is equal to n minus 1 times c sub 1 minus c sub 2. And if we consider this total curvature of the lens, this is a much easier formula to deal with. And if we consider this as just c, we can get p equals n minus 1 c. And this is how optics are normally done. It makes it a whole lot easier to work with. The next step is to find another equation for the radius. Here we have a circle, and we have a chord. That is, we have a radius here and a radius here. This chord is at right angles to this line here. So you have a D here and a D here, which are the distance out to the circle. We have an H here, which is the height. Now we can work out a formula for the radius very simply here. Get rid of some of the circle. Okay, using the Pythagorean theorem, we have r minus h squared plus d squared equals r squared. Expanding that, we get squared minus 2rh plus h squared plus d squared equals r squared. Now we can take this r here, and this r will disappear, and we have h squared minus 2rh plus h squared plus d squared equals 0. So we can get so now we can do put this on the other side. So we have h squared plus d squared equals 2rh dividing by 2h, we get h squared plus d squared divided by 2h equals r. Now, of course, we can also do the curvature this way. We just invert this to h divided by h squared plus d squared equals c. Just turns it over. Here we have an arch, and we're analyzing it. Now, this is really a pretty simple analysis. I'm taking make it out of 3 stones on each side. And the top stone, this one here, all of its weight downward is transferred out. So it would be this little bit out that way, this little bit out this way. Here, the force is actually transmitted in this direction. Okay, so we have a downward force. I'm assuming each of these is 1 centimeter in downward force, whatever 1 centimeter would be. And the outward force here plus the outward force here adds, so your force would actually come like this, but we have to add this bit here, so we get more there. And then again here, we would have the force actually going this way, but it's going to be a vertical force, which is this one plus this one, and a horizontal force, which is this one plus whatever bit we have here. So the result is very much like this. You go, here's your outward force at the top, here's a downward force and an outward force with this one added in, here's a downward force with more outward force, and you can see that a dome like this, a dome or an arch, has actually more outward force than it has downward force, or certainly equal, which is why if you look at them, you will see that most of the domes, for example, in the Parthenon, in the Pantheon, in the Hagia Sophia, they have very solid supports on the outside. You'll also notice that the Romans had something called an oculus, where they would get rid of this part up here, which would, opening it up, what you could do if it doesn't rain very much, gives you much less side thrust. And sometimes also they would put bands around here like this. Now the Gothic arch is better than this. We'll look at that next. So here's a Gothic arch. This would be a 3, this would be a 4, so that the pressure up here, instead of being all to the side, is only 3/4 to the side. And the pressure down here in the middle then takes that 3/4 plus the additional bit, and down here, instead of having equal, we have much less out to the side than we had up here. Resulting in an arch that has less side pressure, so that instead of having to reinforce with lots of material, we can reinforce it with a flying buttress. And that's the main contribution of the Gothic architect. So before we can do any work on this next piece, we're going to need to develop a little bit of preliminary stuff. We want to talk about force, and you've probably seen this before. Mass times acceleration. This is usually in newtons. This is in kilograms, and this is in meters per second. Now, if we have 4 different measures in physics. We have acceleration, velocity, distance, and time that are all related, and we want to get the relation between them. So what we're going to do, we're going to start with distance. Distance equals vt, where the velocity is a constant. And then we can go v equals at. But as time goes on, v gets bigger. So if we have a constant, if a is a constant, this v is not this one. This is a constant v. This is a varying v. But we can get the average v here. And that would be at the time t equals 0, at equals 0, or a at 0, a times 0 equals 0, and a times t equals v. So the average would be 0 plus at over 2. Okay, and that's the velocity we want up here, v average. Okay, so now we can go D equals V average over T equals 1/2 AT times T. E equals 1/2 AT squared. So we're going to use that in just a moment. So here we have a circle with a rod or a string and a weight out here. And what we want to do, if we're rotating around this circle, we're constantly pulling the weight, which would be right here, constantly pulling it back. And the amount we're pulling it is this amount right here. So this is R, the radius of the circle. This, we're going to call VT, is the distance, velocity times t. And we're going to call this little piece down here d. So now we can work out some equations here. So we'll just do the first little piece here, which is using a Pythagorean theorem. V squared t squared plus r squared equals r plus d squared. We'll expand that, equals r squared plus 2rd plus d squared. Okay, now we have an r squared on both sides of the equation. So I'll rewrite it here. V squared t squared plus r squared equals r squared plus 2rd plus d squared. And we can get rid of this. We subtract r squared from both sides. And we get this. Now, what we can do next is we can take our d equals 1/2 AT squared and substitute that in. So we'll have, I'll put it up here, V squared t squared equals 2r AT squared over 2. This 2 cancels. And we end up with RAT squared plus a squared t to the 4th, because this is d squared. Now, we can divide this all by t squared. And if we do that, we have v squared equals RA plus squared d squared. Now we have t only in one place here. Okay, now I'm going to say if t, let's say t is 1/1000th, 0.001. Okay, we're letting time get very small. T is 1/1000th. Then t squared is going to be 0.000001. And if it's a millionth, it will be even worse. so that as t approaches 0, this approaches 0 even faster. And the result is, if we let t approach 0, we get v squared over r equals a. So the acceleration is v squared over r.